Hey, good morning. Uh, so last time we have some exercise on double integral. Is there any question from this part? Can we check the other question? Okay. So please check the other problem. I will also prepare more exercise for chapter 15 later this week. Today I would like to focus. We continue the chapter. So this is the double integral 15.2. I would like to continue to still double integral, but in polar, in a polar coordinates. Okay. So let's start to okay, as an intro. Let me write double integral. So just a reminder that what the polar means is that we are going to convert the Cartesian into polar, which means we are going to see that if we have something in xy, in Cartesian we say, in polar we're going to change into the radius and theta. Okay, and I believe in chapter 10 we already learned how to convert them and learn also how to take calculus into polar. So we can simply convert by taking these formulations. Right? Okay, now for the double integrals, what we are going to see is we are going to convert any curve that we find, especially for the double integrals, we are focused on the area, right? Or if you remember, we focus on finding the dA, right? So something in the region here, for example. Or if you would like to say, so if we have anything like, for example, that defined from this angle, for example, and another angle, let's say this is going to be our theta. And we say that this will be our sector from alpha to beta, and we could find the area inside, right? So what's the idea here is whatever surface you have. So let's say we have a surface on this part here. So anything here. So let's say we have z. Okay. Suppose that this is xy. Okay. We're going to exchange this xy into our r theta. And based on that, we're also going to see that the region or the projection from the surface, we are going to see into the radius and theta as well. Okay. So what we are going to see is we are going to see the rectangular that we find in the regular double integral. This will become a polar. For example, if we take here, let me just, okay, this is just example on R. So we are focused on R. That determines the projections into the xy plane, and we say that we have some R that is defined by the r and theta. and simply say that we can have A, B for R, and alpha from alpha to beta. Or if you would like to cut into pieces, we slice the sectors, and we find out that the small pieces here, this is a building blocks to our integral. Okay, so this is pretty much very similar concept, but the difference is we define now in terms of radius and theta. And also we get this, suppose that the small parts of this building blocks is our delta. So we can have a delta R, which is B minus A divided by how many the number is, or how many the blocks, or we say M. Okay. And the theta is this, the difference in beta and alpha divided by some n, okay, some subinterval n. And let's define the r theta becomes ri and theta j, just to make easier computations. And suppose, let me write here, okay, here. So suppose that the ri asterisk, this will equal with half, meaning that this point in the center, okay, this is, we suppose that this is going to be half the bottom part of the building blocks, which is here, and the top one here. So this will be the half of this distance. Okay? So we suppose that this our definition. And in the same way, we define that the theta j for the sample point of our integrals, this is going to be half so we define these two to help simplify our calculations. And then remember, if we remember what we have in the sector, okay, with an angle theta, we know that, I think from the chapter 10 we also learned that the area is half r squared theta, right? Okay, now if we have this, okay, in our sector, which means that if you want to find the let's say the dA or delta A of this building blocks, okay, it means that we have a large part of sectors. Let me write here. So if we want to find the delta A, so delta A, we can say that this is going to be large sector minus the small sector. Which means that if I draw here to make sure that this is the one that we're looking for. Okay. So suppose that this is the same building blocks as this is. Okay. So we are going to slice this, okay, and then make this into our delta A. So this is delta A. So we could write delta A. The large sector, if you see from here, this is going to be the Ri. Okay. The small sector is Ri minus 1. Okay. So let's write that as our delta A. So half and then multiply with the delta of the theta. and minus same theta, right? Same theta. The difference on it in the radius. And then this will be factorized, and we get this is our equations. And since this is a quadratic equations, a squared minus b squared, we could factorize to a plus b, a minus b. So let's do that. So this will be okay, and then multiply with the delta theta. Now this one here can relate to the delta r, b minus a. So this could be our delta r. Okay. And this part, we intend to get into this definitions. So half ri minus 1 plus ri is ri asterisk. So the whole thing here is ri asterisk. So if we could see from this relations that it seems that the delta A, it's make up the R, delta R, and delta theta. And this will be very important to be implemented in our double integrals. Okay. Okay, and to define this integral, it will be very similar to what we have in our normal double integrals. Let me. Okay. I think I will move this to the left side to make a little bit clearer. Okay. So let me write on the right side. Then we have. Let's say we start from our definition first, from our normal double integrals, just regular one. So f xy, this is delta A, right? Now first we convert into polar. Still this is m, and this will be ri cosine theta j. This is ri sine theta j. Just to change xy into r cosine theta and r sine theta. And then this will be delta A I.
Where's the 1 over 2? Where's the 1 over 2? Okay.
And perhaps if we want to simplify the functions, if this is maybe too long, we can also rewrite f in terms of g. We change to the polar curves. So let's say the g is equal to fr cosine theta r sine theta. So we could rewrite this in terms of g if you want. Okay, and then this delta A, we are going to exchange with this. Well, let me just make it into the right and make it a little bit small. Okay, let me just write first in terms of f, and then later we are going to change all to g. So let's write f ri and this becomes ri delta r and delta theta. So in the definition, let me write a little bit closely. So in terms of definition, similar to what we have in double integrals, so let's so this will be equal to limit. Maybe it makes this a little bit. So limit Sm and n, they are going to infinity. Of f ri we can rewrite this in terms of alpha beta a. We can write in terms of this. So this is our definitions for the polar coordinates double integral. Or you can write here the conclusions. And the left picture is something that you can take as I think a quick recap of what we have done. You can see from our building blocks here. So suppose that this is going to be our part of the sector, okay. And if we define this arc with the r d theta, because the angle we made it into small pieces, okay. We take it as a d theta. So this arc will be r d theta. So basically the area is this dr multiplied with r d theta, or we can just see from our here that this is going to be correct. But the important thing from the formulation is that we need to write the last pieces here. It needs to be written as r dr d theta. If we change r and d theta, it will change the definitions. So it's always start taking theta here, and then the radius is here. So now, if you can see, if some problems can be solved, maybe you can convert them easily to polar, and perhaps that will be a better way to solve it. So some questions, some problems, it's probably easier to solve if we change the conditions into polar. Okay, let's take some few examples. Okay, evaluate. Okay, so evaluate this double integral. And if you would like to see, if you see the integrations, it has the square root of 1 minus x squared, which of course, if you try forcefully do your usual way in this double integral, perhaps you can find the answer. Perhaps you can find easily the answer, but if you notice this part here, I believe that if we convert into polar, perhaps we could see something that much more convenient to compute. So we could start from defining this r. Okay, so start from defining this r. Okay, so this r, so x is -1 to 1, right? So r we can define first, taking the xy, that is x is from -1 to 1, okay, and y is from 0 to square root of 1 minus x squared. Okay. So we start from here. And then we convert to polar. So how to convert to polar? Basically, we are just taking the x, r cos theta, y, r sin theta, and then x squared plus y squared equal r squared. Okay. So first, perhaps, let's visualize the curve. Okay. So we have x from -1 to 1. So let's say this is -1, this is 1. And then we have y equal square root of 1 minus x squared. Okay. So y equals 0 is on the x-axis, right? So it starts from here, right? And then it goes up according to this curve, square root of 1 minus x squared. And if you see square root of 1 minus x squared is perfectly a circle, right? Because you could definitely see that the form is getting this form. But we start from 0, right? Start from 0, and then we get this. So just not perfect. Still not perfect, but I think still okay. Okay, now if we take this, but I think it's not a circle. How about just we take the circle like that, right? And then I erase the part here. Ah, perfect. Okay, so this one is the y equals square root 1 minus x squared. Now if we define this into polar, we know that this is a semicircle, or we could say the circle with a radius 1, right? So we could say that this is having a radius equal 1. And then how about the angle? It starts from, remember the polar, we always start from the polar axis, right? So start from 0, and then pi over 2, and then pi. Okay? So we can say that the theta is from 0 to pi. So 0 theta pi, right? Or we could also say the radius is taking from 0 to r to 1. Okay, and now we can take a new r with r theta. This is going to be our new equations. Okay. So then the question, let's start off from Cartesian. We can convert them into polar. Why? Because we want to compute the integral in much more convenient way. Okay, so this equal, so 0 pi, 0, 1, and then x squared plus y squared is simply just r squared, right? So we could just write this is r squared, okay? But don't forget that this the dA become r dr d theta. Okay. And remember, if you have a functions inside your integral that can be separated, become, for example, if this x and y can be separated, x and y part, you can simply separate the integrations. Okay. So like this one here, we can simply just separate 0 pi d theta, and then this one. So this one is just pi, and then the r cubed become 1 over 4, r with power of 4, with 0, 1 over there, and then this simply just pi over 4. Okay, so if you can compare, if you want to try to force out your weight here, and compare to this like short steps here, I think the polar way or the polar method will be much more convenient. Okay, this is a straightforward questions. So you are getting the equations, the double integrals, and then you convert and find the results. Sometimes the given informations is not enough, so you need to measure by yourself or visualize how it looks like. So you need to define your r, your theta, okay? And yeah, that will be, I think, the more challenging questions. Okay? Let me write below the other example. Find volume of the solid bounded by paraboloid z equal 1 minus x squared minus y squared and plane z equals 0. So first is, I hope still remember what is paraboloid, or if not, then we could trace out the 0 here. We see we move there. We see that it goes to intersect a circle, right? Which radius 1. If this is 0, we see a parabola. If this is 0, we also see another parabola. So we have a parabola like that, with the circle on the bottom. Right? Okay, I hope you can get easily visualize from that. And then z equals 0, so you just have on the ground. So the paraboloid will be sliced at z equals 0. Right? You have like this, and this z equals 0. If you would like to draw, then perhaps this is just a just like that, okay? And let's say this is the axis. Okay? So this is z equal 1 minus x squared minus y squared. Now based on what we have, to find the volume, of course, if you remember, we could define the volume through the z, right? Z, or if you define z as a function xy, we could write this xy, dA, and this is, let's say, d or r. Okay. But if you see any curve that resemble any polar equations within here, if you can see that this r is just a circle, right? And I think for the circle, anything that has relation with circle, I think it's best to take the polar conversion. So this is just a normal circle. So circle is from 0 to 2 pi. And then the radius is just from 0 to 1 because they are just a solid circle, right? So we could take that as well. So from here we could see that the r, this is, and also 0 theta 2 pi. How do we know this? We know this from the trace of the paraboloid itself, okay? So z equal 1 minus x squared minus y squared. When z equals 0, the intersection become x squared plus y squared equal 1, which is a circle with radius 1, right? Okay. Now we could directly write the volume. Let's say this is r. This is 1 minus x squared minus y squared from the equations. This is dA. And we could immediately convert into polar. So theta is from 0 to 2 pi. R is 0 to 1. And then the whole thing inside is just 1 minus r squared. And then r, dr, d theta. Okay. So this r minus r cubed dr. And this will be what, 2 pi, and then half r squared minus half, so half, oh sorry 4, okay, so half minus 1 over 4, 1 over 4 multiplied by 2, so pi over 2. Okay, any questions from here? Okay, any questions? Okay. So I think we can finish the chapter by today or having more practice tomorrow and adding another one that is about the change of variables or the Jacobian transformation. But if we still have time, perhaps, well, let's see if we have time. If not, then we just have a normal exercise. Okay, so if we have another polar curve that we want to measure or we want to evaluate the area between, maybe we have two polar curves. It's pretty similar to what we have before. So we just implement this way here. So if, let's say we have this h1 and h2 as a function from these two polar functions, then we could implement inside our double integral as r. Okay, so this is r. Remember, the polar curves start with r equals something function with theta, right? Remember that the r is function of theta, right? So basically, this h1 and h2 are function of theta, which is r. So basically, you are going to have some evaluation here, and then you need to plug in your h1 and h2 inside, and then evaluate, and then getting the theta. So it's a little bit long process, but still in the polar. So by polar curves, you will see some curves that are familiar from chapter 10, and hopefully you still remember. Hopefully you still remember, so I don't need to review some curves. Some curves is most likely like cardioid, the Rose curve, and so much more. Okay, this is example. We have the, say this is the Rose curve, okay? And then usually in chapter 10 we find the area, right? And then we find the area by taking integrations from this negative pi over 4 and pi over 4 of the polar curve, right? And then d theta, right? But now we could also implement our double integral. For example, okay, let me write here, the four-leaf Rose curve is, let me write here, r is equal cosine 2 theta. So we can define r or d, okay, for the range of all the elements. So for r theta, this is going to be from negative pi over 4 until pi over 4, and then the r is from 0 until cosine 2 theta. Now we could use the definition like when we have in double integral, the previous one, that the area is, we can define through double integral, and then we just take it dA like that. Okay. So similar way to what we have here in polar, we can convert directly. Okay, we can convert directly and use the given informations. So we take r from negative pi over 4 until pi over 4, and then take 0 to cosine 2 theta, and then r dr d theta. And we are going to have some iterations. So we take the inside integral first and then take the outside afterwards. So let me write, this is integral, and then let's process the inside. Let's just complete this work. So we are going to input the answer. So we plug in the point. So let me just write. So this will be, let me just write half outside here, and then the inside will be cosine 2 theta squared, and then d theta. So we need to solve these integrations still. So what's the best way to solve this? Okay. Remember, whenever you have any trigonometric with squared, okay, it's best to remember the double angle. Okay. So we have cosine squared. So we are going to take into, so let's say we have cosine 4, right? So it's become double. So this is called 2 cosine squared 2 theta minus 1. So we have cosine squared 2 theta, cosine 4 theta plus 1, and then divide by 2. So let's exchange this into this double angle. So half I will multiply outside, so it's become 1/4. Okay. And then the whole thing, I will exchange the cosine for theta plus 1, and it will be nicely integrated, right? So we have 1/4. Cosine become 1/4, sine 4t, 1 become just theta, and we need to evaluate this from -π/4 to π/4. And then if you take into sine, this will be practically 0. So we take π/4, so π/16, and then minus π/4. So we take this, and this is going to be π/8. Okay, π/16 plus π/16, π/8, right? And you will see a lot problem like this to be solved by this double angle. So I hope you get the idea on the double angle, and then know how to use it in practice. Okay. I think one more example. We can, if we still have time, we can move to another sections. All right. Another example is find volume of the solid that lies under paraboloid z equal x squared plus y squared. Okay, above the xy plane and inside cylinder x squared plus y squared equal to x. And again, the best way to visualize this is by trying to graph or try to draw, sketch roughly the paraboloid and the cylinder. So how to graph the paraboloid? We can take z as a constant, any number. Then if we see that, if you take this into k, which means that we are going to see in every level, we will see a circle, right? We'll see a circle. Let's say k is equal 1, so we have a circle with the radius 1, and if this is increased, we are going to see that it's going to be increasing in the number of the distance of the radius, right? And then if we take the x or y equal to 0, we are going to see the parabola, right? Parabola. Okay. So perhaps we could start by drawing okay. Start from here. So let's say we have on the top like that. This is a circle. And this will be a parabola. Okay. So this is z equal x squared plus y squared. So without any like the chapter 12 that we have learned before, it's implemented indirectly within most of the questions in the chapter 15. Okay. So yeah, I hope still remember the how to trace the graphs. Okay, now the cylinder. So if you see the cylinder, I think it's best to write in a different form. So we can write in terms of plus 2x plus y squared equals 0. And we can complete the square, okay, if you remember how. So we get just plus 1 plus 1. So this will be x plus 1 squared. So this is another say that we have a circle that has the center of sorry. This is supposed to be negative. So this will be negative. We have a center 1, 0, right? This is circle with radius 1, centered at, okay, now if we take the axis here in the graph, this is y, this is z. So let's say this is 1 here. Let's say this is 1, this is 2. So you have a circle here, that this will be your circle. So where's your cylinder? Your cylinder will be going up there, okay, and going up there. And then perhaps if we take getting through the paraboloid, so we say if we have another circle here that is parallel to the circle below. So if you imagine this paraboloid will be cut through from this side. Okay, if you can imagine. Or I will just give you the clear picture that is, this is the thing that is going to happen. So the solid, the solid is between the top of the paraboloid, the cylinder, okay, and above the xy plane. So this one is under the paraboloid. This is the cylinder, inside cylinder, and then above the xy plane. So this will be our focus. Okay. All right. So then we take the volume as a double integral from some. Let's say we have the D, region D, and then this is going to be x squared plus y squared, and then dA. Now if we define D, let's say in terms of r theta, or let me write first. Let me write that x squared plus y squared is equal to r squared, and x is equal to r cosine theta. So the circle x squared plus y squared equal to x, the cylinder, you can write this in terms r squared to r cosine theta, or r is 2 cosine theta. Let me write this on the bottom there. So if you remember the 2 cosine theta, so we have, so let me just review a little bit. We can have circle here, right? We can have, let me just make it. So we can have here, which is cosine theta, right? Or r cosine theta, or constant cosine theta, right? Or we could also can take it into here, become negative cosine theta. We can take it here, which is sine, or here, which is getting negative sine. So if you take this in here, what will be the angle? So if we want to evaluate this area, the angle, we can start when the r is 0, it's when theta is 0, or theta is pi over 2, sorry, because it's cosine, right? So let me write here, this is, let's suppose that this is going to be 2 r equal to cosine theta. Okay. The theta will be in between negative pi over 2 and pi over 2. Okay. You could say 3 over 2 pi, like from pi over 2 to 3 over 2 pi, but this will be the same for cosine because cosine has a positive value in the fourth quadrants, right? Okay. And so, based on what we have here, we could define some d. So let's say this is d, okay, in terms of r theta. That the theta is between this, okay, and then r is between 0 and 2 cosine theta. Okay, and then we put all this information into our double integral. So theta, we put negative pi over 2, this is 0, 2 cosine theta, and then the x squared plus y squared become r squared, and then r dr d theta. So as usual, we start from the inside, take this is the iterated integral. So take that. So this will be r cubed, so this will be 1 over 4 with power of 4. Plug in 0 to 2 cosine theta, and then d theta. And if we plug in 2 cosine theta inside, we have 16. So 16 divided by 4, we have 4. Let me put outside. And then we have cosine with power of 4 theta. And for the area, we could change also the integrations, become 0 to pi over 2 and multiply by 2. And cosine with power of 4, we could take the double angle formula. So this will be 1 plus cosine 2 theta over 2, and this will be squared like that. So this is, let me write here. This is from cosine squared theta, and then squared. This cosine squared is 1 plus cosine 2 theta divided by 2. Okay. Still, we're still not finished yet. I think let me make it smaller. So this will be equal. So I will factor out half outside. So half squared is 1 over 4. So 8 multiplied 1 over 4 is 2. So that is outside. So the inside will be 1 plus 2 cosine 2 theta plus cosine squared 2 theta. And still we have in d theta, right? Okay, now this part, the cos squared 2 theta, we are going to take another double angle. We get half 1 plus cosine 4 theta, right? So 1 plus half is becoming 3 over 2. So 3 over 2 plus 2 cosine 2 theta plus cosine 4 theta divided by 2. And then d theta. So we integrate all. So we take 2, multiply with 3 over 2 theta. Cosine 2 theta becomes sine 2 theta over 2. So this will be plus sine 2 theta. And then this will be plus sine 4 theta over 8. And I plug in from 0 to pi over 2. So sine 4 theta is become 0. All becomes 0. So this will be 3 over 2 multiplied by pi over 2 is 3 over 4. So 3 over 2. So all becomes 0, right? So this will be the answer. So it's quite long, and perhaps this is going to be an explanatory questions that perhaps a type that probably will be appearing in your exam. I mean, how you solve it step by step. Okay. First, you need to visualize, set up the range between r and theta, and then get into the formulations, and then integrations. So at least 4 steps necessary within this question. Okay, any question? Any question? So I think quite long, and especially every step's taking times. But after this integration, I think should be not really too complicated. I think the most difficult one is to define this one. To define the polar curve. That will be the one that is quite tricky, okay, if you are not able to find any connection between the Cartesian and polar. If you cannot find these relations, it will be very difficult to solve. Okay, I think we can start to see other question as well. Let's start from here. Okay. So for the two questions on the top, it's asking find the volume, okay, given by this fxy, and then this will be the bounded area for the area in the bottom. Okay. So we can start maybe 28, right? 28 or 27. 27 is too simple. Maybe 28. So you have 1 plus cosine theta as your polar curve, and then you have a function that you need to take into double integral, which is just 1. So simply this is just taking, this is d, this is fxy, dA, like that. Okay, which means that we are going to evaluate and find relation between xy and r theta first. So let's focus on on the D. So D, there is no other radius, right? There is no other polar curves, which means that we can say R is just from 0 to 1 plus cosine theta, right? I think that's clear. And how about the theta? I think you can see from this part and this part here, which means that we are going to evaluate from where? Let's say from 0, because when theta is 0, it's going to be 2, right? Which means here, and then that will be 0. So start from 0 to pi, right? Cosine pi, it will bring radius to 0, right? Okay, so I think that will make sense, right? Okay, now next is we take the dA, or the volume. So volume, so this is number 28, so the volume is, so 0 pi, and then 0, 1 plus cosine theta, and then just R, dr, d theta, because the function is just constant 1, right? Okay, and then let's try to finish this off. So let's focus on finding the inside integrations. So let me write here, volume. So R becomes half R squared. And then d theta. And then this will be half. This will be 1 plus cosine theta, and then squared. And then we need to solve this one by one. So one plus 2 cosine theta plus cosine squared theta d theta. So, and then as usual, we take the double angle for the squared, okay, as usual. So you will see in many questions you need to use the double angle formula a lot. Okay, so please remember that. So this will be half. This is 1 plus 2 cosine theta, and then let's exchange this cosine squared to become plus 1 plus cosine 2 theta divided by 2. And then still, this is still in integrations. So d theta. So if we add, this will be 3 over 2 plus 2 cosine theta plus cosine 2 theta over 2. So let's integrate. So this will be 3 over 2 theta plus 2 sine theta, and then this will be sine 2 theta over 2, so this will be sine 2 theta over 4, and then plug in 0 to pi. And then for sine, since it's 0, this will be 0, so we are going to just focus on 3 over 2 theta, which is give you the value of 3 over 4 pi. Okay, for the next question, we are going to see from these 4 numbers from 29 to 32, which one you would like to solve. We have cone, paraboloid, is a plane, and sphere. So for the computation, for the integration, is there anything that's complicated? Still confusing? No? So how about this number, these 4 numbers? Which one would you like to solve? between 29 to 32. 32? 32? Agree, 32? You want to solve 32? Okay. So let's try 32. So try. We'll be giving you a couple minutes first, and then I will give you some hints. And don't forget to try the other as well. Okay? Try the other as well. If you haven't tried some exercise, you'll have some difficulty to familiarize with the problem. So 32, we have a sphere and a cylinder. So if you want to draw, you can draw a sphere with the radius of the sphere is 16 square root 16 is 4, so that's radius of the sphere. And then you have a cylinder. Cylinder that is x squared plus y squared equal 4, or you could say that it's goes to have a circle that has radius 2. So you have a cylinder, okay, and you have a sphere, and it's asking a solid that is inside the sphere but outside the cylinder. So you could imagine like a ball, and you put cylinder inside. Like a hollow ball, but the hollow is a cylinder. What you need to find is the volume outside of that cylinder. So first you need to define r, theta, okay? And then what is the function that you need to evaluate? It's giving you this sphere, right? So perhaps you can see that perhaps z. Let's take z as your function. For function 2 variables. So you have something square root 16 minus this one, because you could convert the x squared plus y squared into r. Right? So that's probably a good way to take this function. Right? Yeah, but I think I get the idea. Okay, so if we take the sphere like that. Okay, and then we have we have 2 is maybe here. Okay, so this will be circle. So we take the cylinder like that. Okay, first of all, the sphere is going to intersect the xy within the circle, right? So this will be x squared plus y squared equals 16, right? For the one that is intersect in the xy plane, the sphere. So let's make the z as a function of xy. So we could write z in terms of 16, or maybe let me write z squared 16 minus x squared minus y squared, or z is square root of 16 minus x squared plus y squared, like that. Okay. Okay. So what we are going to find. Okay. Let me write this in this area here. Let me rephrase this, and it's become like this. Okay? So the small circle is going to be our cylinder, and the large one is the red one here is our sphere, which means that this will be the radius 1, this is radius 2. Okay? And the theta is just all theta, right? 0 to 5. Okay, so this will be R1, which is 2, right? This is R2, which is 4, right? This is R equal 2, this is R equal 4, right? Okay. So we could take the volume as, we could take this from 2 to 4, okay? And since we have, okay, if I'm writing just this, and then from 2 to 4, this is just evaluated from xy plane to this top, right? But we have the bottom one, so we need to multiply by 2. You get the idea? Okay. So we need to multiply by 2. And then evaluate the double integral from this 4 to 16, or from radius 2 to 4. Okay. And let me write in terms of xy first, and then we convert to polar. So convert to polar, conversion to polar. And this will be 16 minus r squared, and then r dr d theta. Okay, maybe if you're still wondering what's happened with these two, this is because usually we take this like that, right? We evaluate this something over the surface, right? But we have another one that is below, right? Because it's a sphere. So we need to multiply by 2. And then I think you can solve this. Okay. Take the substitution, right? For r squared, r, you can cancel r, okay, and then the rest you can try to integrate. But I think the idea is to get this idea and then multiply by 2, that is the main goal. Okay, we can continue tomorrow for more practice, and we can go to the we call the Jacobian transformation, which basically this r dr d theta, this is also, we can say that it's coming also from the same transformation, the Jacobian. So we are going to see tomorrow. Okay, if there's no further questions, let's go to the feedback question. Okay.